is Mr. Kevin. Is nuclear power good for the environment? Our lifestyle is very heavily dependent on the electricity. I don't think I need to elaborate too much on that point. All my experience, of course, relates to the UK, and I'll mostly be talking about the UK. And in the UK, we could have blackouts pretty soon if there isn't something being done to replace aging plant. Our coal plant is being shut down. In fact, just last week, for the first time since the beginning of electricity generation, we had 24 hours without coal being burnt to generate electricity. And the coal plants are all being taken offline, partly for environmental reasons. And of course the nuclear plants are also aging, and they'll all be gone within certainly 10 years, apart from Sizewell B, if they're not replaced. And of course we don't want coal or oil to generate electricity. Gas is a bit cleaner, but when I say it's running out, I basically mean UK's own gas supply is running out. Come to that later, but there's still plenty of gas about in the world. Renewables, of course, are very much flavour of the month, but the problem with renewables, the wind doesn't always blow, the sun doesn't always shine, and of course they are also expensive and take a lot of subsidy. So the question then is nuclear the answer? And as we know, safety and waste disposal are matters of public concern. How serious are those concerns? But first I want to talk a little bit about global warming. Now, this graph shows the global average surface air temperature since 1850. Now, it fluctuates naturally. When I first started to study this particular aspect of climate change over 30 years ago, I was a bit skeptical because there is a lot of natural variation. I know that the theory says that carbon dioxide should heat the atmosphere, but was there enough? This theory has been around for over 100 years. Swedish chemist Sven Arrhenius, he did some sums about 100 years ago, more, and concluded that there really wasn't enough carbon dioxide being produced artificially by burning coal and whatnot to have an impact, and that was true at that time. And the question is, what has been happening since? And you can see a bit of an upward trend there, but there is also a fluctuation. But since 1990, the change has been quite dramatic. And that's largely due to the rapid industrialization in China and India. But what really convinced me about the link between carbon dioxide concentration and global temperature is this graph. You can see the fluctuations in global temperature. You can see the carbon dioxide concentration. This is measured at an observatory called Mauna Loa, which is in Hawaii, and those measurements have been carried out since 1960. Measurements prior to that can be obtained from ice cores, particularly the Greenland ice cap. And that correlation to me is dramatic. So I'm in no doubt now about the reality of climate change. The projections, well, they depend on what we can do about mitigating carbon dioxide production. And those projections there come from an international committee that has looked at this issue. The International Committee on Climate Change looked at different scenarios. The different color codes there represent different scenarios depending on whether we've got high economic growth or low economic growth, whether we have a lot of investment into carbon limiting, or whether we do very little. Either way, we're locked in. Even if we stop producing carbon dioxide now, what's already in the atmosphere will continue to heat the atmosphere for some time. It takes about 100 years for the levels to reduce again. But we will continue emitting more, and the temperature will continue to rise. The Paris Agreement of 2015 aimed to stop the rise at 2 degrees, an average of 2 degrees. However, if we fail, if the temperature rises by more than 3 degrees, now it doesn't sound a lot, but it is, it may become unstoppable because of feedback effects. Several feedback effects. Melting the polar ice cap changes the albedo. That's the ability of the Earth's surface to reflect. So the whiteness of the ice cap reflects sunlight. The Arctic Ocean absorbs probably about 5 or 10 times as much energy from the sun as the ice would. And we're seeing the minimum ice on the Arctic Ocean last summer was something like, the area was about half what it was 30 years ago. And the volume of the ice was about, had fallen by about 75% compared with 30 years ago. So the ice is not only less in extent, but it's also thinner. So that's a problem. Another problem is the permafrost in the tundra. As it melts, it releases methane gas, and methane is a very powerful greenhouse gas, much more powerful than carbon dioxide. Similarly, warming the oceans releases carbon dioxide and methane dissolved in the ocean. So these effects accelerate global warming. A 6-degree rise would be equal to the Permian extinction of 250 million years ago, when 90% of marine species disappeared, and I think 70% of terrestrial vertebrate species disappeared. So there's no doubt that human activities have changed the chemical composition of the atmosphere, and that there is an identifiable change in climate. We may have reached a tipping point. That's what I mean when I say it could become unstoppable due to feedback effects, positive feedback. There are other environmental problems with fossil fuels. Particulate emission from coal-fired power stations and from diesel engines causes problems with lung cancer and cardiovascular disease. Sulfur dioxide is responsible for acid rain, but for the most part we've now pretty much contained sulfur dioxide by cleaning it up. It's much more difficult to deal with nitrogen oxides as well as particulates. And the OECD estimates that air pollution is responsible for something like 800,000 premature deaths annually worldwide. I think the figure for the United Kingdom is 20,000. This compares the gaseous emissions from different fuels. Coal produces a lot of carbon dioxide, obviously, so oil a little bit less, natural gas less still, and of course nuclear as with renewable sources of energy such as wind and solar, none. And lesser figures for sulfur dioxide and nitrogen oxides. You can deal with sulfur dioxide, you can strip it out, you can deal with nitrogen oxides. Dealing with carbon dioxide is much more difficult, partly because of the huge amount of it, and partly because we don't know what we would do with it if we did strip it out, except possibly stick it into disused oil and gas wells. So the UK is a net importer of oil and gas, and that of course makes us very vulnerable to the people that supply it to us, primarily in the Middle East and Russia. And another interesting fact is that China is commissioning 2 new coal-fired power stations every week. So even though we're shutting down our coal-fired power stations, the Chinese are, vastly outweighing any advantage that we might get in terms of, and of course it is a global effect. I mean, what we do doesn't just help us, it helps the world, but what the Chinese do also affects us just to the same extent. Another issue, of course, is that oil and gas prices are volatile. A few years ago, it looked as if they were going through the roof, and that would make renewables and nuclear power much more viable economically. Now they're not so much, because gas in particular, and oil from fracking, is very plentiful, which 10 years ago we didn't see coming. I mentioned the Paris Agreement in 2015. Ironically, just as the agreement was being reached, the next day Germany opened a new coal-fired power plant. The thing about Germany is that they are so totally opposed to nuclear power. Angela Merkel, of course, was quite in favor of it until the Japanese Fukushima disaster. And then she sniffed the political wind and almost overnight changed the policy to shutting down their nuclear power stations. And of course, they're replacing them with coal-fired power stations. Some renewables as well, but coal-fired power stations are bad news. And of course, another problem, if you are dependent on Russia for your gas supplies, you can suddenly find that the tap's been turned off for political reasons, and that has happened in the last few years. The current situation in the UK is that coal is around 22% and falling rapidly, gas 29.5% and rising rapidly, nuclear 20% and falling, be down to about 5% within 10 years, unless we do something. And the renewables is currently around 24%. And the difficulty with that is, how do you actually increase it? Because the more renewables you've got on the system, the more difficult it is to keep the system stable because of the interruptible nature of renewables, the variable nature. That's just an indication of the gap between UK gas and its production and its demand, and the extent to which we're dependent on imports. I mentioned carbon capture and storage. This is a sort of schematic idea that you could use a power plant not only to produce electricity but also to produce hydrogen, for example. If you wanted to use hydrogen as a liquid fuel in liquefied form for, you can use it for various forms of transport. And then you have a plant for separating the carbon dioxide, and then you stick it into old oil or gas wells. The renewable sources of energy: wind, wave, solar, biomass, geothermal, and tidal. a lot of people think that they're the solution, and they are part of the solution. But I don't think there's any scenario that you can come up with that you can run an economy entirely on any of these renewable energies, particularly the unpredictable ones, wind, wave, solar. Tidal, it's variable because obviously the tides vary, but at least it's predictable. But something that's intermittent in a random way, it makes it very difficult to deal with. And it also means that you have to have some form of backup form of generation for when it's not there. And people will tell you, oh, but there's always some part of the country where the wind is blowing. Yes, that's true, but you can't move your wind turbines around. So if you want to be sure of a megawatt of power, and you've got a wind turbine that produces a megawatt, you've got to have several of them in different places. And even then, there are times, particularly in the winter time, in the dead of winter, when you get an anticyclone over the country, there's not a breath of wind anywhere across the British Isles. That can happen. So you can't depend on wind. Sun doesn't shine very much in the winter time, and not at all at night. The economics of new build were looked at by a committee of the Royal Academy of Engineering in Britain. This is a few years ago. And they compared different forms of advanced coal-fired with integrated gasification and carbon capture, and other forms with different forms of coal and gas-fired combined cycle, and compared them with renewables. And this little bar here represents the additional cost that you have to put onto renewables to allow for standby generation for when the renewable isn't actually there, which makes all the renewables much more expensive than coal, and nuclear comes in as competitive with gas. Well, that's no longer true because gas has got cheaper and nuclear has got more expensive. And I'm going to show you this. This is a more recent cost estimate produced by the British government, and the cost of Hinkley Point, it's very much higher than the cost estimate from the Royal Academy of Engineering. They have in fact taken what is called the guaranteed strike price for Hinkley Point C. That's the price that the government has guaranteed to EDF, who will build Hinkley Point C, £92.5 per megawatt. Now that price is slightly less than the guaranteed strike price for renewable energy such as wind. It's just slightly less. And it's a very generous price. It's for that particular plant. The plant is the first of a kind. If they go on to build another plant, such as one proposed for Sizewell C, then the price will come down. But for that plant, it's guaranteed for 40 years. Oh no, sorry, 35 years. And it's a very generous price. Meanwhile, the other costs, they've got very much lower costs for wind and solar, but curiously, the costs that they've put into that table are not the current strike price that they're offering to contractors. They are projections for a future price, whereas the nuclear price is not a projection for how it might be in 10 years' time after we've built a whole lot. I'll come back to that point. I just want to talk about waste, because waste is a big issue. Now, the volume of solid waste from a coal-fired power station for 1,000 megawatt or electric power per year, as you can see, it's 3,000 tons of solid waste. This is ash. Forget the carbon dioxide, which would be sort of 10 times or more. The amount for nuclear, of course, is much, much smaller. Another point I want to make about nuclear power is that it can be used for a whole range of things. You can use it for electric heating, but you can also use it for transport if you use it in the form of either electric batteries or hydrogen-powered vehicles. And aviation kerosene can be replaced by liquid hydrogen. But what about radioactive waste? Nuclear waste is highly toxic. Yes? I think we can agree that. And it lasts for 1 million years. That's what we're told. Is it true or is it false? Well, I can tell you something about other forms of toxic waste. Heavy metals such as cadmium, lead, mercury. They're highly toxic and they last forever. But nuclear waste decays. This graph shows the decay of fission products after fuel has come out of a reactor. And the decay is very rapid within the first few years. After 10 years or so, it has dropped to about 10% of its original level. And then it's sort of after 30 years, it has kind of leveled out at around 3 or 4% of its original level. And what's left is longer-lived wastes. Still, the largest of those would be wastes that would decay over a period, well, with a half-life in the order of 30 years. Things like strontium-90 and cesium-137 will continue to decay, leaving you much longer-lived wastes, which I'll come on to in a moment. But if you take all the fission products from the amount of electricity equivalent to one person's lifetime, so think of how much electricity you will use in your lifetime, and all produced by nuclear, the spent fuel converted to fission products, the fission products converted to a vitrified form, it's a lump of glass, that would be the lump of glass that represented the fission products from your contribution over your lifetime. That's just to show you how small a volume it actually is. The radiation continues to decay. The previous graph showed the first 30 years. After that, well, we've got sort of 100 years, and then we've got 1,000 years, 10,000, 100,000, 1 million years. And as you can see, it is continuing to decay over that kind of time scale. And after 1 million years, there is still some radioactivity left. But in fact, by 5,000 years, the amount of radioactivity in the spent fuel is less than from the ore from which it was derived. So really, the statement that nuclear waste lasts for millions of years is somewhat specious. Nevertheless, you do have to take care of it. Generally speaking, we've got an enormous amount of waste accumulated in the UK. When I say enormous, I mean relative to what we would produce in a new generation of power stations. There's a lot of waste accumulated in tanks at Sellafield, gradually being converted into vitrified form for long-term storage. And a new generation of power stations would add only a small amount to that existing waste. Now the reason for that is that the original Magnox power stations didn't produce a lot of electricity from a given amount of uranium. They were pretty inefficient. They only converted about 0.5% of the uranium to electricity. So you had to use a lot of uranium to generate the electricity. We can do a lot better than that now. And a lot of other processes that were used in relation to the Cold War for nuclear weapons also produced wastes, and those wastes still exist and have to be dealt with. The long-term management is that for high-level wastes and the more radioactive of intermediate-level wastes should be stored deep underground and in a manner that keeps it separate from the environment for 1 million years or more. Now, I said that the amount of radioactivity after 1 million years is very, very slow, very, very small. But the fact remains that the view is taken that it ought to be kept from, isolated from the environment for that length of time. And that's not difficult, theoretically. Proving it, of course, is always a problem. But the bigger problem is actually getting people to accept it. It's a political problem. It's not a technical issue, really. It's a political problem, and the government is still wrestling with how to get communities to accept it. And one way, of course, is to provide them with financial incentives, which some people say, but that's bribery. I know that in Ireland there's always been a lot of concern about the discharges from Sellafield. And this graph shows two different sorts of radioactivity. The top graph is the alpha activity. Alpha is the more toxic of the activity. Comes from things like plutonium. And at one time they did discharge substantial amounts into the Irish Sea. The expectation was that it would be diluted and dispersed and would disappear into the oceans at a level that would be of no concern. The reality is that 90% of all the plutonium ever discharged from Sellafield is sitting on the seabed within 10 miles of Sellafield. And that came as a bit of a surprise. However, they introduced new technology at Sellafield in the 1980s to separate any residual plutonium from the effluent stream that was being discharged, so that what has been discharged in the last 30, 40 years is almost insignificant in terms of its radiological impact, health, environmental impact. And it will stop completely in another 10 years or so when they complete the reprocessing program. Low-level waste is another issue. Low-level waste is the sort of stuff, laboratory trash and the sort of stuff that gets contaminated with radioactivity in the course of a working day. And it's like any other kind of landfill. At least it used to be. And it doesn't look good. So, again, about 30 years ago, when all this sort of stuff became very controversial, they introduced a different approach. They packaged the waste in these freight containers. They're called ISO containers because I think International Standard Organization defines freight containers. And they're packed into that and then filled with a cement grout so that the waste is immobilized. And then they're stacked in a vault. and the vault will eventually be capped. And the intention is that that waste will decay over a period of about 300 years to insignificant levels. And that's it. I mean, that's the low-level waste repository for the whole of the UK. And that's the current vault that's open, but some of this land around it represents vaults that have been already capped and sealed. For the higher level wastes, for the really dangerous stuff that has to be kept isolated for tens of thousands of years, arguably up to 1 million years, the idea of a deep repository, perhaps as much as 1 kilometre deep, and isolated from groundwater by various means, using bentonite, for example, or clay. So, moving on, what about Chernobyl? I mean, Chernobyl was a big shock. Everybody has a picture in their mind of a disaster, a nuclear disaster that could happen with a power station. I mean, the worst power station disaster that ever happened is one that didn't actually happen. It's a fictional one from the China Syndrome, the movie. And that made a big impression on people, and that's still the picture that people have in their heads when they think about disasters. 3 Mile Island was a trivial disaster in comparison. There was very little release of radioactivity. Nobody was hurt, as far as I know. Chernobyl, very different. It was an explosion. It wasn't a nuclear explosion. You can't have a nuclear explosion with a nuclear reactor. It's just not physically possible. It was a steam explosion, but nevertheless, it released a large proportion of the reactor core and the fuel into the atmosphere and spread it around, well, certainly around Europe. And I think we still have controls in sheep production in parts of Wales and Cumbria because of the radiation released from Chernobyl. 28 people died from the immediate effects of radiation and thermal burns. Another 19 died from long-term effects. And there have been about 9 deaths from thyroid cancer, but of course the number of thyroid cancers has been quite large. I think something in the order of 1,000 thyroid cancers that have been attributed to Chernobyl, but mostly thyroid cancers are curable. The official death toll from the fatalities from Chernobyl is 56, which is by far the worst there's ever been from any nuclear accident, but very small compared with other industrial accidents such as, Piper Alpha, or in India, the chemical plant, what was it? Bhopal? The Bhopal. Thousands of people killed in that one. So as an industrial accident, it's quite big, but not the thousands of people that you will read about if you go on the internet. Chernobyl is associated with many thousands of deaths caused by extrapolating the effects of very low-level radiation on the basis of no threshold. We don't know what the threshold might be for exposure to radiation, so we assume there is none when we do our safety assessments. So if you take a very small risk to an individual and multiply it, a risk of say 1 in a million, and you multiply it by a large number of people, say 50 million for the population of Britain, you get a finite number, which is 50. So you say, well, the risk, 50 people will die as a result of that exposure. Now that is equivalent to saying that 50 people will die as a result of everybody smoking one cigarette. It's exactly the same arithmetic. And the same arithmetic applied to particulate diesels, particulate emissions from diesel engines, gives you not 50 but 20,000 a year. So whatever we might think about the risks of Chernobyl, they are relatively small in comparison with other things. That's not to say that it's tolerable. I mean, Chernobyl is an accident that shouldn't have happened and couldn't have happened with a Western-style reactor, because there are characteristics of that design of reactor, that Russian design of reactor, that would not have been allowed to have been built in the West. In fact, they actually based it on the design of the World War II piles that were used for making plutonium for the first nuclear bomb at Nagasaki. And it has a characteristic known as a positive void coefficient, and it's something to be avoided. However, as far as Chernobyl is concerned, there's no evidence of birth defects. We're told about the terrible effect of birth defects. There's no evidence of adverse effects on pregnancy or of genetic changes being passed on, no effect on decreased fertility, and the only radiation-induced illness that has been observed is thyroid cancer in the general population, either in the contaminated areas around Chernobyl or further afield. And if you want to know more about all of that, you'll find that the International Atomic Energy Agency has produced a very detailed study on that, which is where I got my information from. So, what are the plans for building new reactors in Britain? When I first started talking on this topic about 10 years ago, I was saying quite confidently that we would start building Hinkley C in 2012, and by 2017 it would be operating. I can now tell you that they did start building it last month, and we're hoping it will be operating by 2025, followed by Sizewell C. I could also have told you that we were confident that we would have some advanced boiling water reactors built at Wilfa and Albury by Hitachi. Hitachi are getting nervous about that. And the reason they're getting nervous is that the third project, by a consortium led by Toshiba and GDF Suez, which is now called Energy. Energy has pulled out of the consortium, and Toshiba is reviewing its options because they have lost, they bought Westinghouse, and then Westinghouse, they bought another American contractor called Stone & Webster, and then when they opened the books for Stone & Webster, they discovered that they had bought a lemon, and they're taking a hit amounting to billions of dollars. And as a result, they can't afford to build these three AP1000 at Cumbria. And they're trying to sell that project to the Koreans. And the Koreans are saying, well, we don't really want to build AP1000s, we want to build our own reactors. These are the different power station sites, both existing shutdown ones and proposed new ones, but time's moving on, so I better leave it at that. Hinkley Point, the plan is for two 1600 megawatt PWRs, which between them would be 7% of UK energy demand. It's a French design. I've already talked about the controversial contract terms giving guaranteed price. somebody's worked out that that represents a return on equity, depending on how things play out, depending on what happens to the price of electricity, for example. It could be a return on equity of somewhere between 20 and 35%. Now, I would really like to get that on my savings instead of the miserable 0.5% that I currently get, but it doesn't seem to be that easy. As I say, the contract has been signed, the first concrete has been poured, completion maybe 2025, followed by size we'll see. The problem with this, it's called the EPR design. The problem is that it has been designed to deal with every possible event. Earthquakes, we don't get many in the UK, but nevertheless it's been designed to deal with earthquakes. Aircraft crashes, well, you know, after 9/11, people really got worried about the idea of a jumbo jet being flown into a nuclear reactor, obviously, and so it's been designed to deal with that. External explosion, extreme weather conditions. I mean, we saw the problem at Fukushima with the tsunami. And electromagnetic pulse is something that could either occur naturally from the sun. The famous one in, when was it, 1860 something, that took out the transatlantic cable. You know, a massive solar flare. Could happen. Could be struck by a comet, for him. But you know, every conceivable event has been sort of thought about and designed against. That, of course, has made it enormously expensive. So much redundancy and so on. The Westinghouse AP1000, it's meant to be a simpler and safer design, but it's still what we call passively safe. You know, you'll be able to walk away from it. I mean, the big problem that people perceive with the current generation of pressurized water reactors is that if you have a loss of coolant accident, that you know, it can be catastrophic. You can get a meltdown. With this, you've designed it in such a way that you can flood the reactor with water from a tank, borinated water, to kill the reactor. Of course, once you've done that, you don't have a reactor anymore, but it pretty much guarantees that you won't get a meltdown. But again, these things all make them more expensive and more difficult. At the moment, there are 4 AP1000s being built in China. I don't think they're operating yet. I've said their operation, that's a bit out of date. I think there have been some delays, but they are getting close to completion. There are 2 in the USA which are behind schedule. Small modular reactors is very much fashion at the moment to talk about. The British government has set up a project to put about £250 million into R&D. The idea being, I mean, we've been building small modular reactors in the form of submarine reactors for the last 50 years. The idea is that you would build them in a factory and then deploy them wherever you want. And they could be ideal for small countries like Ireland, anything up to 300 megawatts, which is about 1/10 the size of Hinkley C. The traditional economies of scale that you get with a big plant, you would look to get from small modular reactors by simply building them in large numbers. But it hasn't happened yet. So suppose we wanted to combat global warming by having a very high nuclear strategy. Instead of 10-20% of our electricity coming from nuclear. Suppose we said, like in France, they've got something like 75%. Suppose we said we wanted to get 75% of all our energy, not just electricity, but domestic heating, all the rest of it, from nuclear electricity, and the other 25% from renewables. How would you do that? Well, there are currently 440 power reactors operating worldwide, and there are about 60 under construction, mostly in Asia. And that represents about 7% of total energy requirements. If we wanted to go for a high nuclear strategy, we would need something like 3,000 large power reactors to produce just 50% of total energy. Is that possible? Can we do it? Is Federlin Eyanif. In summary, nuclear power produces no gaseous or particulate emissions harmful to the atmosphere or to human health. The volume of solid waste from nuclear power is much smaller, although obviously much more hazardous, than from coal-fired plant. Although I should add to that that when they considered building a coal-fired plant at Sellafield, they realized that the ash and coal contains enough natural radioactivity that we would have to define it as low-level waste. Disposal of nuclear fuel and the other radioactive wastes is a political problem. It's not a technical one. And in summary, nuclear power, in my view, is clean, is safe, is carbon-free, and can be made cost-effective. Thank you.